Okay, so this first problem says scouts at a camp shake the rope bridge they have just crossed and observe the wave crest to be 8 meters long. 8 meters is roughly from here to the wall. Okay. If they shake the bridge twice per second, what is the propagation speed of the wave? Okay, so here's the rope bridge that's shaking, and the wave crest to be 8 meters apart. So here are the crests, and these crests are 8 meters apart. And they shake the bridge twice per second, so the frequency is 2 hertz. Okay, 1/second is hertz, and that's 2 seconds. Okay, so the wave speed is just wavelength times frequency. The wave's speed of any wave is frequency times wavelength, so it's 8 meters times 2, 16 meters per second. And 16 meters per second is about 40 miles an hour. Okay. So easy problem. This one says, what is the wavelength of an earthquake that shakes you with a frequency of 10 hertz and gets to another city 84 kilometers away in 12 seconds? Okay. So the distance traveled by the wave is speed times time. So the speed is distance over time, 84 kilometers divided by 12 seconds. So that's the speed of the wave. Okay. And this is equal to, so 7 kilometers a second. This is called P waves. They're primary waves, which are longitudinal waves. And it shakes with a frequency of 10 hertz. So speed is frequency times wavelength. So wavelength is speed divided by frequency. So 7 into 10 to the 3 meters per second. And frequency is 10 hertz. Okay. So wavelength is 700 meters. Okay, so 700 meters, the wavelength is from here to that Krispy Kreme shop. Yep. Yep. All right. Your ear is capable of differentiating sounds that arrive at each ear just 0.34 milliseconds apart. So, okay, so here's one of the techniques. If you close your eyes, you can tell where a speaker is from the time difference of the sound that comes. Okay, so for instance, if the speaker is in front of you, the sound reaches both the ears at the same time. And so you know it's in front of you. If it's behind you, it's got to go through your head, and then you know it's, even though the time is, okay. If it's to your right, it reaches this ear first and that ear second. Okay. So that time difference is long enough for you to tell if that the speaker is on the right. It turns out that underwater, sound travels 5 times faster. So now this time difference is 5 times smaller. So underwater, you can't tell where the sound is coming from. Okay. All right, so that's what this is. So your ear is capable of differentiating sounds that arrive at each ear about 0.34 milliseconds apart. Now, actually, it's your brain that is telling you, so that's a little typo, but which is useful in determining how low frequency sound, where low frequency sound is originating from. Okay, so suppose a low frequency sound source is placed to the right of a person whose ears are approximately 18 centimeters apart, and the speed of sound is 340 meters per second. How long is the interval between when the sound arrives at the right ear and the sound arrives at the left ear? Okay, so here the head of the person, this sound arrives, and then that sound. Okay, so let's say this is distance d, or we'll say delta d. So delta d to cover that distance, this is the extra time this guy needs. Okay. So the time difference in arrival of the sound between the left and the right ear is delta d divided by v. So you see, larger the speed, smaller the time difference. Underwater, the speed is 5 times greater and the time difference would be 5 times less. Okay. So in air, that's 18 centimeters, which is 0.1 meters, and the speed of sound is 340 meters per second. Okay, so the time difference is 0.53 milliseconds. Plenty of time for your supercomputer to process that information. Okay. Now, underwater, the story is different. Underwater, that speed is larger, and that time difference is smaller. Okay. Assume the same person was scuba diving, and a low frequency sound source was to the right of the scuba diver. How long is the interval between, if the speed of sound underwater is 1500 meters per second? Okay. So you already know the answer. Okay. So delta t is 0.18 meters divided by 1500 meters per second. .12 milliseconds. Okay. So to tell where the sound is coming from underwater, you would need a faster processor. Okay. Any questions? You guys understand? Okay, we'll talk about more directional things next chapter, chapter 17, when we do this chapter on sound. Okay, this problem says a pulse can be described as a single wave disturbance that moves through a medium. Consider a pulse that is defined at time t equal to 0 by this equation. Okay, so if you plot this, you can go use a spreadsheet or whatever to plot it. And if you plot it at t equal to 0, this will look something like this. At x equal to 0, and by the way, so if you notice this unit, this is in meter cubed, this is meter square, so meter cubed divided by meter square is meters, so that's in meters. Yeah. And for x equal to 0, that's 6/2, that's 3 meters. So the amplitude is 3 meters. Okay. So that's how the pulse looks like. The pulse moves with a velocity of 3 meters per second in the positive direction. And you want now this pulse to move in that direction at 3 meters per second. Okay. What is the amplitude of the pulse? You already saw the amplitude of the pulse is y x equal to 0 equal to 6 over 2 equal to 3 meters. Part B, what is the equation of the pulse as a function of time? So how do you write the equation of the pulse as a function of time? What do? We talked about this last time. I'm sorry? I'm sorry?
Fx plus vt.
Minus vt. Very good. Okay, so it's f of, wherever you have x, you replace that by minus vt. Okay, so this would be 6 over x minus, and v is 3 meters per second. So here is a pulse that's moving to the right at speed v. And if you wanted to have it move to the left, then it would be v plus x plus 3t. Yeah. Where is the pulse centered at 5 seconds? At 5 seconds, 3 times 5 is 15 meters, so it's centered at 15 meters. Okay. So this pulse would be there where this is 15 meters. Okay. At 5 seconds. All right. Okay, so if you become an electrical engineer and stuff like that, you will learn signal processing, and this could be a signal that you want to travel. You want traveling down your fiber optic cable, let's say, okay, without distortion. And for that to happen, you learn to do Fourier transforms, and all frequencies need to travel. You don't have to have dispersion. All frequencies will need to travel at the same speed and all that kind of stuff. Okay, so you're being set up for future courses. Okay, so here's another similar problem. A pulse is defined as that. Okay. So there's 2t, so let me write this without units. So here's a traveling pulse. It's a function of x and t. Okay. E to the power minus 2.77 2x minus 2t Okay, so if it's a function derived from that, and that's a Gaussian function, okay? So, and this essentially looks like the same function like that, except that it falls off steeper, okay? So it looks something like that, okay? All right, what is it that I want? So what is this pulse doing? It's traveling to the right at 2 meters per second. Okay. Use a spreadsheet or other computer program to plot the pulse as the height of the medium y as a function of x. Plot the pulse at t equal to 0. So essentially at t equal to 0, this would be 0. It would be 4x squared by 5 and 4x squared by 25. So yx at 0 is e to the power minus 2.77 times 4 over 25 x squared. Yeah. So let me simplify that. Okay. So this is yx0. This is how the pulse looks. Okay. Where is the pulse centered at t equal to 3 seconds? At t equal to 3 seconds. It's centered at 6 meters. Okay. Do you guys understand all of that? All right. Okay, so here's a cosine wave. A wave is modeled with the function yx t equal to 0.25 times cosine 0.3x 0.9 t plus pi by 3. Okay, so you saw that this is a sine function or a cosine function traveling to the right. And here's the standard form. A is the amplitude, cosine or sine kx minus omega t plus phi. Okay, so your function is, the amplitude is 0.25 meters. Amplitude is 0.25 meters. That's that big. Okay, so that's a large amplitude. That's sort of like a water wave. K, the wave number is 0.3 meters, 0.3 1 over meters. Omega is 0.9 1 over seconds. Omega is in radians per second if you want. And that is the phase constant. Okay. All right. So, and this problem is about identifying all the quantities. So, what is the amplitude of the wave? A is 0.25 meters. Yeah. What is the wave number? K is the wave number, which is 0.3 1 over meters. Okay. And if you guys remember, K is related to the wavelength like so. Okay. And you can check your notes about that. C, the angular frequency, omega is 0.9 1 over second, and omega is related to linear frequency like that. What is the wave speed? Wave speed, the speed at which that wave is traveling, is omega by k, or frequency times lambda. Okay, so in our case, omega is 0.9 1 over second, and k is 0.3 1 over meters. So it's 3 meters per second. That's the wave speed. Okay. E, the phase shift is pi by 3. Okay. The wavelength, k is related to the wavelength like that. So lambda is 2 pi by k. 2 pi divided by 0.3 1 over meters. And so that is equal to essentially 6 pi. All right, I'll go to the next page. Wave, wavelength is that. And the period of the wave, the period omega is 2 pi f. And period is 1 over f equal to 2 pi over omega. What does the period tell you? It tells you how long it takes for one wavelength to travel. It tells you the time for one oscillation, okay, and so on. And this is equal to omega is 0.9. So essentially 7 seconds. Okay. All right, so really what this problem was about was if you have a sine wave traveling to the right, this is the standard form of the equation, sine or cosine wave. That's the amplitude, that's the wave number, that's the angular frequency, that's the phase shift. Okay, so you have to know how to identify all those things. Okay? And how these guys are related to the speed and all that. Okay? So this equation, this function contains all the information about the wave. Okay? And you were to tease out that information. Okay. You guys understand? Any questions on that? All right. Yeah, this problem says a piano wire has a linear mass density of mu is that's 10 to the minus 3 kgs is grams. So essentially 5 grams per meter. So this wire weighs, a meter long wire like that weighs 5 grams. Okay. Under what tension must the string be kept to produce waves with a wave speed of 500 meters per second? Okay. So the speed is related to the tension and mass per unit length like that. Okay. So you know the wave speed, you know this mass per unit length, and you can calculate the tension. Okay. So V square mu times V square equal to the tension. Okay. So that's 10 to the 2, 10 to the 4 will kill that. So you're left with 10. So that's 49.5 times 25. Okay, and that'll be in newtons. So the tension okay, so that piano wire is under tension of about 1300 newtons. That's about twice your weight. Okay, so those piano wires, there's a metal frame that's holding that tension. Okay, and you don't want piano wires to snap. Okay. Does anybody play the piano here? All right. So 2 strings are attached between 2 poles separated by a distance of 2 meters. So again, 2 meters is like from here to the edge of the table. What?
No.
All right. 2 meters probably is the tallest person in this room, that fella there. What's your height? 6'7". 6'7"? All right. So he is 2. Yeah, he is 2 meters. 6'9" is 2 meters. You should be playing basketball instead of golf. All right. Two strings are attached between two poles separated by a distance of 2 meters, as shown in the preceding figures. Both strings have a linear density of 0.0025 kg per meter. The tension in string 1 is 600 newtons, and in string 2 is 700 newtons. Okay, so will these two pulses travel at the same speed? The strings are made of the same material, same thickness and all that. This tension is higher. The tension is higher, the speed is higher. So this pulse will travel faster. Okay? Transverse wave pulses are generated simultaneously at opposite ends of the string, so you generate them simultaneously. How much time passes before the pulses pass one another? Okay, so let's say they pass at this location. And you guys know that this location will be past midway point because this guy is traveling faster. Okay? That is 2 meters. Let's call this distance x. So x is v1 times t. The pulse 1 reached there at time t. In that time, how much did the pulse 2 travel? When this guy traveled x, so they have met there, so this guy traveled 2 minus x. Okay? Okay. X is what we're trying to find. How much time passes before the pulses pass one another? Time is what we're trying to find. Okay. So what we'll do is we'll substitute for x in there like that, and then we'll get an equation in t. So 2 minus v1t equal to v2t. 2 equal to v1 plus v2t. Okay, and this makes sense. This guy's traveling at v, this guy's traveling at v2. Their combined velocity has traveled a distance 2 meters. Okay, that's what it's saying. Okay. Now we just have to find the velocities. Okay. All right, so v1 is tension and mu is 2.5 into 10 to the minus 3 kg per meter. Yeah. So V1 works out to 490 meters per second, and V2 is 700 divided by 2.5 into 10 minus 3. Okay, so those are the speeds. And so they meet after 490 plus 5. Okay, so 2 milliseconds later. Okay. Any questions on that? All right. The note E4 is played on a piano and has a frequency of 393.88 hertz. If the linear mass density of the string of the piano is that 0.012 kg per meter, so a meter of that string will weigh 12 grams, and the string is under a tension of 1,000 newtons. What is the speed of the wave on the string and the wavelength of the wave? Okay, so the speed of the wave is tension divided by mu. And so here's how you could do it. This, say, 12 times. So this is 10 to the 3, 12 times 10 to the minus 3. And that comes to the top. 10 to the 6 square root of that is 10 cubed. So this is 1,000 divided by square root of 12. Okay. So the speed of the wave on this piano wire is 288.7 meters per second. Okay. So what is the speed of the wave of the string and the wavelength of the wave? The wavelength speed is frequency times wavelength, and wavelength is speed over frequency. So the wavelength is 0.73 meters. Okay, this problem says a string of length 5 meters. 5 meters is roughly the height of this room. Yeah. And a mass of 90 grams is held under tension of 100 newtons. 100 newtons is 10 kgs hanging on it, about 22 pounds. Okay. A wave travels down the string that is modeled as that. What is the power over one wavelength? Okay. So tension is 100 newtons, and a wave is traveling down this thing. So the wave is given by that 0.01 meters. That's the amplitude. Sine 0.4 x minus 170.1. Okay, there's t is missing there. There should be a t there. And phi is 0. Okay, power is 1/2 mu v. Power is the energy traveling per second. Okay, and is b a square omega square. If you check your notes, here's where the formula is. There. Okay, so that's the rate at which this wave is carrying energy per second. Okay, and okay. Oops. Okay, so power is energy passing per divided by time, and so one wavelength will calculate the energy carried by one wavelength of the wave. Okay, how long does it take for one wavelength to pass a given point? It takes a period. Okay. All right, and the period is related to frequency like so. Okay, so power is 1/2 mu v a square omega square e times frequency. Okay, so the energy carried by one wavelength is 1/2 mu v by frequency. Okay, so we'll do that. All right, and actually, so we'll do this. Frequency is omega is 2 pi f, so frequency is omega by 2 pi. So we'll cancel one of the omegas. This is omega by 2 pi. We'll get the 2 pi over there. The 2 will cancel, so let me do all of that. Energy is 1/2 mu v a square omega square. F is omega by 2 pi, and the 2 will cancel, one of the will cancel. So energy is pi mu v a square omega. So that's the energy carried in one wavelength of the wave, and that's what's traveling. Okay. Now it's just a matter of looking at this equation and figuring out all the quantities. Okay. All right. So all right, so now let's E is okay, so mu is 5 meters and 0.9 and 90 grams. So mu is 90 into 10 minus 3 kgs divided by 5 meters. Okay, so that's 18 times 10 minus 3 kg per meter. Velocity of the wave is tension divided by mu. It's 100 newtons is the tension divided by 18 times 10 to the minus 3 kg per meter. Okay, that's the velocity. So what all do we have? We have mu, we have v, we have amplitude, and we have omega. Okay, so now let's put everything together. So energy carried by one wavelength of the wave is pi mu is 18 times 10 to the minus 3 kgs per meter. Velocity is 74.5 meters per second. Amplitude was 0.01 meters. 0.01 meters, 1 centimeters, half an inch, a little less than half an inch. And omega was 1170. Yeah. And all those units should work out to joules. Okay, so that's 10 minus 4, 10 minus 7, and we'll make that 10 minus 4. So 10 minus 4 joules pi into 18 into 74.5 into 1.17. Okay. Okay, so 0.5 joules. That's what it works out to. So it's carrying half a joule of energy. Yeah. So, I mean, this kind of calculation would be useful if, let's say in Star Wars, you have these laser guns. You shine a laser for half a second, how much energy have you deposited on your enemy if all the energy got absorbed? Okay. You're trying to shoot down a satellite. How much energy do you need to deposit to shoot that thing down, to melt that, okay? Or you're trying to cook a pizza using a laser. All right. All right, ultrasound of intensity, 150 watts per meters. Okay, what this means is if this ultrasound beam was a meter by meter wide, the energy being sent is 150 joules per second. Watts is joules per second. Okay, 1 meter by 1 meter. If the ultrasound beam was that wide. Of course, the ultrasound beam is of a medical imaging device 3 centimeters by 5 centimeters. It's about 1 inch by 2 inches. Okay, that's how big the head is. What is its power output? Okay, so intensity is power divided by area. Okay, intensity is energy power per unit area. So power of the device is intensity times area. And so power is, intensity is 1.5 into 10 to the 2 watts per meter square. And area is 3 times 5, that's centimeter square, 10 minus 4 meter square. 10 to the minus 2 meters is a centimeters, and you square that, that's 10 minus 4. Okay? So that is 15 times 15 is, 15 times 15 is 225. Okay, so 225 into 10 minus 3 watts. So 225 milliwatts. Okay, that's the power of this thing. You guys have seen those little red lasers? That's 5 milliwatts. Okay, let's see, what is this laser? This guy is dangerous. No, it says less than 5 milliwatts. That's not right. Maybe the print is too small for me to read. Those little red lasers are 5 milliwatts. Anyway, all right, we'll stop here.